Hello, my name is Reagan Miller, and I am a first year grad student in the FOSS group. And I am here today to talk to you about my project on spiropyrin fluorescent sensors for single molecule barium detection. So the first thing that comes up when thinking about this project is what exactly a spiropyrin is. And so in this first section here, we are able to see that the characteristic of a spiropyrin is this pentagon sharing a single carbon with this hexagon, as it is highlighted here in red. As we can see, there are three different variable R groups that could be adjusted in the spiropyrin for this project, which we will talk about here going forward. But what we need to know is on the left, this spiropyrin is known as in the ring closed position or the fluorescence off position. And on the right, we have our ring open and fluorescence on position. So spiropyrins have been used in liquid phase as chemosensors for metal cations, but have not been used in gas or dry phase detectors, which is what our group is aiming to make our sensors able to do. The reason we are looking specifically for barium 2+, or as we call it in the group, barium tagging, is to enhance searches for neutrinoless double beta decay of atoms, the decay of xenon gas. And so the traditional way of viewing this is xenon decaying to barium 2+, as well as 2 nus and 2 betas. Fluorescence in these molecules depends on barium binding within the crown ether binding domain, which we will see here in the next section. Whenever barium is bound to this crown ether, we change the binding of the spiropyrin as well as the conformation of the molecule itself. So the first thing that this project had to deal with is design of the spiropyrin molecular scaffolding. And so in this, there are variable R groups. As we can see here on the left, we have R1 and R2. R1 can either be something as simple as a methyl or as complex as a long chain alkyl group. R2, we are looking at adding electron withdrawing groups, as well as looking at what it would be if it was just a proton. The reason we're looking at electron withdrawing groups is the idea that it might stabilize the open ring formation. Also in this figure, we're able to see our open crown ether. And then once we introduce our barium, the barium binds within this binding pocket or binding domain. And as we can see here in our characteristic spiropyrin, without barium present, our spiropyrin is closed. And then with barium present, our spiropyrin opens up. One of the reasons we're looking at spiropyrins as a fluorescent molecule is previous literature has shown both its reversibility as well as its intense reaction to metals. And then even more so, it shows that the transfer from the off state to the on state repeatedly can happen without photobleaching. So as we can see from this paper from 1998, without metal, our ring is in the closed or off state. And then with metal, we have intense fluorescence whenever the ring is open. Continuing on, then we had to look at how to make these molecules. And so we are looking at a convergent synthesis pathway. First, making our pentagon side, which is shown here in red, and then making our hexagon side attached to the crown ether, which is shown here in blue. We've done the first step of the synthesis, resulting in 75% yield. And then once we're able to create our pentagon side and our hexagon side, we'll be able to link them together in an easy synthetic way that just takes 18 hours. Something that's interesting to note here is because of our convergent synthesis, we are able to change both R groups relatively easily because they're at different points in the synthesis. Eventually, we want to immobilize our molecule on a transparent substrate surface in a monolayer fashion, and we specifically are looking to add our molecule onto glass. So as we can see here, we'll have our non-fluorescent spacers, which will allow us to do single molecule detection, as well as we have our molecule added onto a linker. Here is the instrument that our physics collaborators have made, where once we immobilize our molecule onto glass, we'll be able to put it under vacuum for single molecule fluorescent studies. So in summary, we're looking at various synthetic routes that have variability at multiple points in order to find the best detector for barium 2+ ions. Once we're able to create our molecule, we'll be able to immobilize them on a glass surface, and then they'll be tested under vacuum for molecule imaging. Thank you for your time, and I really appreciate you listening today.